In this unit, we're going to take a look at units, the units we use in physics, how we convert between units, and what must be true of units before we can combine them. So let's start with our standard units. Our standard units, we only have 3 because we're really concerned with measuring 3 different dimensions, and then we can derive things from there. So the first unit we are interested in measuring is length, how far things are from each other, and we measure this with meters. Meters gets abbreviated with an M. Now, the other 2 units are mass. Remember, mass is the amount of matter in an object. Don't confuse it with weight. Mass tells me how much matter is present. This is measured in kilograms. Now, I know grams is the base unit, but we want everything in kilograms because grams are fairly small, and we're going to be dealing with things that are fairly large most of the time. And then finally, we have time. Time is measured in seconds. And seconds gets abbreviated with in lowercase s. Now, those are our standard units. They're called standards because they're all based off of a standard somewhere. Mass is based off of a hunk of platinum. Length is based off of how far light travels in a given amount of time. And time is based off of the energy or radiation emitted from a cesium atom. You can get into that if you'd like. Now, we can take those units and combine them in different ways to measure different things. For instance, length is just a measurement of a distance from one point to another. But we can extend that and try to measure an area, right? And now I have a length and another length, and now I have an area. And that area will have units of square meters. And length times length gets me meters squared. Or I could extend it again into 3 dimensions, and then I could have a volume, which would give me cubic meters, right? Length times width times depth. So now I'm talking about 3 dimensions. But I don't just have to combine 2 of the same units together. I can compare a length in meters to a time in seconds, and I could tell a speed, or I could give that a direction and have a velocity. So I can combine those as well. This is a derived unit because it's made up of units that are standard units. So we can do that, but we've got to be careful because this division is okay that these dimensions don't match, right? This is the dimension of length, that's the dimension of time. I combined them even though they don't match because I'm comparing a length to a time. But I can't do something like add a length plus a time. That doesn't make sense. It doesn't make sense to add 15 seconds to 10 meters. So in order to add or subtract units, the dimensions must match. So, and I said units, but I meant measures. Measures must be of the same dimension in order to add them or subtract. Now, what I mean by that is we've got to add lengths to lengths and times to times. We can add velocities to velocities as well, and we can add forces to forces, but we can't add times to masses. Doesn't make sense, right? Got to be in the same dimension. Now, the other thing that should be true before you add them up is the units should also match. Okay? And what I mean there is we can't add meters to centimeters because centimeters and meters have a different length, right? 1 meter is about this far. 1 centimeter is about that far. So if I want to add 10 centimeters to 2 meters, I need to have both of those, even though they're both measuring a length, to be in the same unit. And for that, I need a unit conversion. Now, for the metric system, that's pretty easy, right? Because we have kilo, hecta, deca, base, deci, centi, milli. And I could say, all right, well, I want to put centimeters in base units, so I've got to go 1, 2 places to the left, and I could say this is 0.10 meters, and I could say 2.1 meters, right? I don't need a conversion factor for that, but I'm going to show you how a conversion factor works. A conversion factor is a well-chosen 1, and what I mean by that is we can multiply a measurement by a conversion factor, which changes the unit, but it doesn't change the value because it's just a 1. And so let's go back to this example. I know that there are 100 centimeters in 1 meter. This is my conversion factor, and it can make it 1 because if these are equal to each other, if I divide either side by itself, what I do to one side I have to do to the other. So like if I decide that I'm going to divide both sides by 100 centimeters, what I'm left with is 1, because centimeters cancel centimeters. 100 divided by 100 is 1. 1 is equal to 1 meter per 100 centimeters. So this is my conversion factor, or it could be, but I could have divided the other way and I could invert that. And that is going to mean that if I take 17 centimeters and I multiply it by 1 meter per 100 centimeters, I haven't changed anything except the unit, because this has a value of 1. I'm multiplying by 1. However, that centimeter cancels that centimeter. 17 times 1 is 17, so I have 17 meters over 100, and that's equal to 0.17 meters. And so just like I moved my decimal 2 places left, I can do that with my conversion factor as well. Now, it's silly to do that in the metric system, because it's the metric system. It's all based on powers of 10. You just got to move your decimal point around. But if I wanted you to convert, say, inches to centimeters, then you would need to know that conversion. And it's true that 1 centimeter is equal to 1 inch is equal to 2.54 centimeters. So you do need to know, I'm going to rewrite that, 1 inch equals 2.54 centimeters. That will allow you to convert inches to centimeters, but also centimeters to inches, right? You just have to decide, are we going to divide by centimeters to get centimeters to cancel, or are we going to divide by inches to get inches to cancel? So conversion factors, once you have it like this, you can use it either way to get either unit in your conversion.